Howdy, people. Let's talk about the motion of a projectile. In particular, let's talk about the motion of a projectile whose path or trajectory is symmetrical. And what I mean by that is this object lands at the same height it was launched from, as you can see in our little diagram. So, here is a fundamental fact about projectiles. Projectiles move in the kinds of paths that they do, called parabolic paths, because of two important facts. And those facts come from, or can come from, an analysis of what's going on with this object at any and every instant that it's going up and coming down. Well, here's the object. Here's the object at any one of those instants. Okay, no matter when we're analyzing, at any and every location on this trajectory, there's a force acting on this object. And there's only one force. And that force is a gravitational force downward that has that size, mg. That force depends on how massive our object is, and g is the strength of Earth's gravitational field. Okay, so mg is this object's weight. It's how hard Earth's gravitational field pulls on that object. So at any and every instant, this object, well, any and every instant after it was shot and before it hits the ground, so not before it's shot, not after it hits the ground, just after it's shot, there's the only force. There's the only force, 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 there's the only force until just, okay, then it hits the ground and then the ground pushes on it. But while it's a projectile, mg is the only force acting on this object. Okay? Now I will grant that some of you people who are looking at projectile motion stuff haven't talked about forces specifically yet. But that's okay. Some of you have. Now, Newton's second law says that how hard an object is pushed is related to how fast the object accelerates. And in particular, not only that, but how hard an object is pushed, say, in the horizontal direction dictates how fast it accelerates in the horizontal direction. And the same thing can be said in the vertical direction. How hard something is pushed, you know, as a combination of all the forces acting on it. It's what sum of all the forces. How hard what the size of that combination of forces dictates how fast the object accelerates vertically. So, if we look at our free body diagram here, there are no forces in the x direction. The object's mass isn't zero, so that says that this object has a horizontal acceleration of 0, or massively important, v in the x direction is constant for any projectile, neglecting air resistance, of course. That's a huge fact. All right, so look at here is a vector component, or a component of this initial velocity v naught that we'll call vx. All right, now we can say at any instant and every instant that here's our object, right? Here's our, yep, good. Here's our here's our object. Come here, object. And now I'm going to take these two dudes. Hang on. Get over there. There you go. At any and every instant that this object's moving, its horizontal velocity is that big, 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 that big. All right? Now, velocity is not a force, all right? So that's why it doesn't go in our free body diagram here of saying, but it's pushed downward with a force mg. Yeah, okay, but it's not pushed sideways, so it can't change velocity sideways. Okay, so what I'm going to do is say it's worth saying that now that's the horizontal velocity. At the very end, just before it hits the ground, that's the horizontal velocity. At the top, that's the horizontal velocity. Okay, at anywhere you want, that's the horizontal velocity. Okay, a little trigonometry says if we look at this, Vx is part of a right triangle that contains V naught and let's call it V initial in the y direction. That's a V naught y. v naught y. A little trigonometry says that a right triangle can be made out of vx and v naught y and v naught, and vx is v naught cos theta, v naught y is v naught sine theta. How come I'm not saying v naught x? Well, since vx never changes, there's no real reason to talk about how fast it was initially. Okay? It never changes. We can just call it the horizontal velocity. All right. Now, notice here that if we look at our net F in the y direction, we get there's always this downward mg force. So the object is always accelerating downward at a rate of g. Ay is g. Downward. Which means that g is two things. G is the strength of Earth's gravitational field near the surface of the Earth, and therefore how fast objects accelerate when they're placed in Earth's gravitational field. Sort of coincidental, sort of not. So, what that means is, over time, here's what happens. Don't draw there. We're gonna need that space later. Over time, object's velocity changes at a constant rate vertically, but doesn't change at all horizontally. So, well, here's an interesting place in a trajectory right there. The interesting thing about that place is this object has gotten to the top of its path, and for one instant is not moving vertically. Vertical velocity instantaneously is 0. Okay? So we could start to do things like say, well, how long did that take maybe to get to the top? Let's do that. Let's do that. Let's say time to the top. All right, well, time to the top, here's what we can do. We can use a kinematics equation that says this. V final is V initial plus AT. If we're going to do kinematic stuff in 2 dimensions, what we have to do is limit ourselves in any single kinematics equation to using variables in 1 dimension. We can't mix horizontal velocities and vertical accelerations. We can't mix vertical displacements and horizontal velocities. All right, so using those subscripts is a great way to make sure you keep everything in the same dimension in the same equation. All right, we happen to know that at this top place, I'll put here top, that's 0. All right, so if I'm going to solve for t to the top, I get t is negative v initial in the y direction divided by a in the y direction. It's okay? Which says that t to the top is v naught y negative v naught sine theta. So this is our top left trig expression. There's a time to the top. Why is that negative there? Well, that negative is there algebraically because of we subtracted that to that side. Physically, here's the deal. This is the initial vertical velocity, and that's upward. G is the acceleration. That's downward. If we are treating these quantities as vectors, which we have to when we write a kinematic solution, we have to account for differences in direction with sign. So either v naught, typically what you do is say upward is positive, downward is negative, so G is negative 9.8 or 10. But then there's this negative algebraically here, so that negative and the negative here for G cancel out, and time is left as a positive number. Good. Okay? Okay. So, that says we know how long this thing takes to get to the top. Super. All right, that's something that maybe is of some value. I'm going to come back to this in a minute, because what if we wanted to say, I'm on to the next slide. What if we wanted to look at the time this thing spends in the air? T total. All right, well look, here's v initial y. Some of you maybe are saying, well, wait, isn't the total time trivial because we know how long it takes to get to the top? It actually maybe is, but I want to prove it to you, and I want to do it like this. If we say, well, what do we know about now? This instant at the end. All right. The one thing we know is, well, here's this Vx. Here's this Vx that's the same size. We don't know how far this is, delta x, so there's no way to analyze the vertical stuff. All right. Sorry, there's no way to analyze the horizontal stuff, but here's something that we know. All right. If this thing lands at launch height, landing at launch height, that means delta y total is 0. Sure, this thing goes up in the air. Sure, it comes back down. But if we're talking total, we say compare now vertical position to now vertical position. Those two vertical positions are the same position. And if we say delta y total is 0, watch what we can do. We can say there's a kinematics equation that we write like this, delta y meaning change in vertical position, v initial t plus 1/2 a t squared, but let's make sure we're saying in the vertical. Delta y is sort of like saying change in position in the vertical, but instead of saying delta xy, we just call it delta x, or delta y, why not? Okay, well, check it out. Delta y is 0. I can subtract v naught t from each side, v naught y. And look, there's a common factor of t on each side. And if I solve for time in the air, multiply both sides by 2, divide by g, because ay is g. Or we can expand a little further and say negative 2 v naught sine theta. So this is our little trig work from before. And look at this. Look at the previous result, time to the top, negative v naught sine theta over g. Look at total time, negative 2 v naught sine theta over g. Right? This is the time to the top. Time to the bottom is the same as that. So this thing spends a certain amount of time going up. It spends the same amount of time going down, which tells us a couple of things that are real important. All right? It tells us that, well, remember, since this thing moves at a constant horizontal velocity, and we can say delta x is vx times t, since vx is constant, change in horizontal position is proportional to how long this thing travels for. All right? And so since from here to here is half the time, and here to here is half the time, and I'm justifying that by saying we know t to the top was this. The total time in the air is twice that, thus t from top to bottom is the same as t from bottom to top. Okay? It means that this point here, the apex, is exactly halfway along this horizontal displacement. So I'll call this delta x 1/2 and also delta x 1/2. Since horizontal velocity is constant, we get the same distance traveled in each of those halves of the parabola. Okay, here's something else we can say. And again, I sort of mucked up I'll go to a new slide. Ready? Okay, so if we go to this slide, well, here's our initial vertical velocity, v naught y. Well, in some amount of time, that vertical velocity changes to 0. Now again, here's half the time. Here's the other half the time. In some amount of time, velocity changed from initial to 0. In the same amount of time, the vertical velocity is going to change by the same amount. And that's because AY is constant, and that's delta Vy over t. All right, or delta V in the y direction is AY times t. Since g is constant, it means that how much velocity changes is proportional to time of flight. So in one amount of time, velocity changed from this to nothing. In the same amount of time on the way down, velocity's got to change from nothing back to this, but in the downward direction. That's our constant vertical acceleration of g. So here's v final y at the end. Check this out. So this tells us something important. These two vectors have the same length. Those two vertical components of velocity have the same length, and that happens to be true at any two places that are at equal heights. So now say, here's our here's our object, and now say, here's our object, and now, well, hang on, watch this. Here's how I do this like pretty darn accurately. Watch this. Here's horizontal velocity component. Oh boy, horizontal velocity Vx. About that big. Fine. That means horizontal velocity now is still that big. It means it's still that big. It means it's still that big. All right. Right now, the whole velocity is about this big. Notice how I'm drawing it tangent to the curve with the right size x component. Tangent to the curve with the right size x component. And now look, vertical velocity now has to be about that big. Here has to be about that big. And look, these two things are the same size. At any vertical equal position, we'll have the same vertical velocity. Here's something else that's pretty cool. Oh boy. Because at the beginning, our initial velocity has the two components that you see here, Vx and V0y. And at the end, Vx is the same. V final y is, well, the same size. It means that this total, that total velocity has the same magnitude as V0. So V, magnitude of V and magnitude of V0 are the same thing. It lands at the same speed it was launched with. And actually, this angle and this angle have to be the same too, because they're two equal sides of two similar triangles. There's quite a bit in there, huh? What we didn't do is say, what's nice to be able to talk about is there's still Vx at the top. Okay? Now, in terms of solution stuff, we've only really talked about, I mean, this is a big one. This is something people that write questions, will want you to be able to state. All right? That's the total time that a projectile spends in the air, assuming it follows a symmetrical trajectory. Okay? That's a very useful piece of information, because what if we wanted to say, talk about how far something went, delta x total? Well, the only way to handle any delta x stuff is to do that, which again comes from that greater kinematics equation where ax is nothing, so that whole term goes. All right, so look at this. We can write this expression delta x is Vx times t. Well, here's our t from the previous slide. So there's a way to find time in the air. And I should put a V0 here. Very good. Okay. Now, I know how to manipulate this because I've been at this a while. It turns into this. -2, there's this 2. And then I got a V naught in each of, I got a V naught here, I got a V naught here. That's V naught squared. Oh wait, hang on. Let's do this. How about we do this? We take the V naught squared first. I got the negative. There's the V naught squared. Here's the 2. And then I got a sine theta from the right-hand term. I got a cos theta from the left-hand term. All right, fine, over G. Now, the truly, well, never mind. Some among you, you won't know. That's a trig identity. 2 sine theta, cosine theta. That is equivalent to, hang on, V naught squared. That's the same as this. In green parentheses here, in blue now parentheses here, that's the same as this. So says trig. If you know, yeah, fine. It's a trig identity. There's a, I don't care to do the trig part here, but that's a true statement. All right, and the nice thing about this expression, you typically won't get this on a reference table sort of thing, but it is handy, and it shows us something really cool. It shows us something that says, if we want to shoot this thing as far as we can at some given, we got a cannon that shoots things at 1 speed, right? What if we want it to go as far as we can? Well, what angle do we shoot it at? Well, it means we want the stuff in the blue parentheses to be as big as we can make it. It means we want the sine of something to be as big as we can make it. Well, a sine function can be as big as 1 when the thing you're taking the sine of is 90 degrees. So that says delta x max at 2 theta is 90 degrees, or when you shoot at 45 degrees. And that's not a wildly strange thing to guess, right? And the reason for that is, a 45 degree launch gives you equal sizes of V naught x or V naught y and Vx. This means it, goes pretty high and spends a good amount of time in the air, but it also goes nice and fast horizontally, as opposed to say, well, I shoot it way high in the air, but I only go slow horizontally, or it never gets up very high, so doesn't spend very long in the air, but it sure goes fast horizontally. Yeah, but it wasn't in the air long enough to go very far. So the 45 degree launch is your angle for maximum range. Nice little piece of trivia. This also shows you something that's really cool, and it can come from a little analysis of a sine curve. In particular, all right, the part that goes, here's theta. Here's, oh no, here's theta. This one be theta. This one be sine of 2 theta. Now, this is 1. And this, you know what I should do? How would I do this? Let's make this 2. Yeah, sure, 2 theta. Better. There's 2 theta. I want to do that. Nope, go back to making that theta. Yeah, okay. So, check it out. If theta's 45, right? Here's 45. The sine of 2 theta, so that's the sine of 90, yep, is 1. Good. All right? Now look at this. Check out how these 2 arbitrarily chosen, here's a number. I don't know, what is it, 0.6? Sure, fine. Well, look, we get 0.6 as a sine of 2 theta out of this angle and out of this angle. And this angle is a certain number of degrees away from 45, and that's the same number of degrees away from 45. Maybe this is, I don't know, 15 degrees, 30 degrees away, and this is 75 degrees, also 30 degrees away. Those 2 angles have the same value of sine 2 theta, the same value that goes in here. That means that, okay, we're saying let's shoot something at the same speed. There's 2 different angles that can get us the same exact range, because the quantity in here gives us the same amount. And notice, sure, saying they're equal distances from 45, but also, what's true about 15 and 75? Oh yeah, they add up to 90. Right? If we took two other rando angles, like, I don't know, this one's 8 degrees away from 45, and this one's 8 degrees, well, that's, oh boy, 37 and 53. Well, those also add up to 90. All right, so one thing you can do is if you want to get two projectiles to land at the same place, you can shoot them at complementary angles. Right? So this one, this angle is, I don't know, what do you think that angle is? It's big, 60. So if we shot another one at the same exact speed, but at a 30-degree angle, what it does is the path doesn't look the same, right? It goes and lands there. This one goes hey, and this one goes meow, but they both get to the same exact place. They don't make those noises necessarily, but they do have the same range. All right, so what I would write down here is complementary angles, complementary angles yield the same delta x. Pretty neat, huh? Yep, it is. The one thing we have not talked about yet is, how do we talk about this peak location? All right, this peak location. Well, here it is. This one's really not too bad. This is what I would call delta y max. All right, how high is that? Well, that depends. How fast was this thing shot upward? That's all it depends on. All right, we got to use our known fact about this location here, that vertical velocity is 0 for an instant. Then we can use this kinematics equation. Well, let me do this. Let me say v. Let me say v squared, good, is v naught squared plus 2a delta x. I'm going to call it delta y, thank you very much. Now, we got to make sure we're only talking about quantities in one direction, one dimension. And we use the fact that at that instant, we can stop analyzing there if we so choose. That goes. That makes this, by definition, delta y max, because we're saying when the vertical velocity is 0. And this becomes delta y max, not too hard to solve for. Negative v naught y squared over 2ay. Or delta y max is negative v naught sine theta squared over 2g. And again, why is that negative up there? This negative here, well, again, v naught sine theta is v initial in the y direction. That's upward. G is downward. Those have to have opposite signs. And so then this negative goes away with perhaps the negative in G here. Okay? Okay, so this one maybe I should have done a few minutes ago, but it tells us how to find that delta y max. All right? This is, really where the big detail kind of work is. Pretty neat stuff about horizontal range. Here's stuff about general symmetry of these paths and what that means about velocities at different instants. Here's how a real important one about calculating how long this thing spends in the air. All right, and here's sort of fundamentally where we started about why does a projectile follow a path like this? Well, it's because it's constantly accelerating downward, but not accelerating at all horizontally. Okay? And being able to identify these as the ways to express components of velocity is the same thing you would do when you're finding components of forces. Okay, like so for example, we know that at the top right now, this object's total velocity is v naught cos theta. Right? We can tell how fast this thing goes at the top if we knew how fast it was launched and at what angle. Okay? So a lot there, folks. I hope you learned something. Bye.